Hey, welcome to Passages in Applied Mechanics by Dr. Lorenzo Garcia. Today, dynamics. Mechanical energy. We have already seen how doing mechanical work can later affect the condition of a physical object. Do you remember? How does this object move when we apply a force? It moves to the right, right? At least if we apply enough force. We can do mechanical work also by lifting an object to a higher elevation against the force of gravity, isn't it, or by accelerating the object against the inertia of its mass, such as kicking a ball or stretching or compressing a spring against the ability of its material to resist such deformation. It took many centuries of scientific thought to recognize that the work done to lift or to accelerate a body, or to stretch a piece of elastic material, does not disappear without a trace, but is in fact stored within the body by reason of 1. Its increased elevation above some datum level. 2. Its higher linear or rotational velocity, or 3. The amount of elastic deformation produced. At least in theory, mechanical energy is fully retrievable in the form of work if the process is reversed. You can think, for instance, of the sport of archery. All bows consist of a string attached to elastic limbs that store mechanical energy imparted by the user drawing the string. We will discuss this example further later, but let us define, firstly, mechanical energy. Mechanical energy is usually defined as a physical quantity stored, and it is the measure of the capacity of the body to do work, so the unit of energy in the international system is the joule. By the way, did you know the word of energy is derived from the Greek meaning neuro gamma epsilon iota alpha, energia, and has no direct translation to English? It is frequently described as being at work. Stored energy is always latent, so not directly observable or measurable. Then, how could we evaluate it? As engineers, do we like to quantify stuff, don't we? In this case, we will be using measurements of other related physical quantities, such as mass, height, velocity, and elongation. Intriguing? We will talk about it shortly, but let me point out something before. The effects of energy in action are always obvious, for example, a drop hammer driving a pile into the ground, or a joystick mechanism driving by a spring. The amount of energy can be taken as a measure of the amount of energy released. Hey, let's do something. Stop this video now, and try to visualize this mechanism. Are you able to see the controller or the joystick from the picture? Look at the index finger. Yep, you got it. It is true that in most practical situations friction appears to detract from the quantity of work available when stored. Some energy is inevitably converted into heat and dissipated, but we could include those effects in the overall energy later. But to start with, let us begin by ignoring it, and focus in three forms of mechanical energy: gravitational potential energy, kinetic energy, and elastic strain energy, in the absence of frictional losses. Potential energy. Potential energy of a body is the energy that a body possesses due to its position in the gravitational field. Let's consider a block of mass m, raised a distance h, above the ground. The force of gravity acting on the block is F, due to the weight, W equal mass, m, times the gravity, g, and the work done in lifting the block is W equals Fh equals mgh. This work is stored in the body as potential energy with respect to the ground as the datum. In symbols, potential energy can be stated as W equals Fh equals mgh. Pe equals mgh. Note potential energy could sometimes be expressed as Ug, or even U, etc. It will depend on the author and text, but the important thing here is to understand the definition behind and the concept, okay? It is also interesting to note that the earliest concept of potential energy goes back to Galileo era, who recognized that when a load is lifted with a pulley system, the force applied multiplied by the distance through which that force must be applied, remains constant even though the force and distance may vary. It was a fascinating discovery to use in our favor as engineers. How? Gravitational potential energy has a number of practical uses, notably the generation of pumped storage hydroelectricity. It is also used by counterweights for lifting up an elevator, crane, or sash window. Roller coasters are an entertaining way to utilize potential energy. Another practical use is utilizing gravitational potential energy to descend downhill in transportation, such as the descent of an automobile, truck, railroad train, bicycle, airplane, or fluid in a pipeline. Next time you cycle downhill without pedaling, you will feel the potential energy. Kinetic energy. Over the course of dynamics, we found that in order to accelerate a body in linear motion, work must be done on that body. As a result of doing W units of work, the velocity changes, so that the quantity m times v squared over 2 was first recognized in the 17th century and was called vis viva, or from the Latin, living force. Curious, isn't it? In the 19th century, it was finally accepted that vis viva was not a force, but a form of mechanical energy now called kinetic energy. The kinetic energy of a body is the energy which it possesses due to its velocity. Kinetic energy is proportional to the mass and the square of the velocity. In rotating bodies, can also be calculated using rotational analogues of the linear terms mass and velocity, namely mass moment of inertia, I, and angular velocity, omega, as. A windmill is one of the examples of applications of kinetic energy, and in this case, in rotation. In a windmill, when the wind, which is air in motion, hits the blades, it causes rotation, which ultimately leads to the generation of electricity. Here, the moving air has kinetic energy that causes the rotation of blades, and therefore, in this example too, the kinetic energy is converted into mechanical energy. Similar to the case of a bicycle, when a person riding a skateboard is at rest, the kinetic energy will be zero. As the skateboard moves, the kinetic energy gradually starts increasing. Similarly, when the weight of a skateboard's rider is coupled with the high speed of the board, a large amount of kinetic energy is generated. And what about walking or running? When walking or running, we possess some amount of kinetic energy. This is why we feel comparatively warm while running or after walking some distance. Sweat is the result of the heat produced by our body due to running. While walking or running, there is a conversion of chemical energy into kinetic energy. How did say our body is not a machine? Hug. Strain energy. We are ending with the third form of mechanical energy, such as that stored in and stretched or compressed. A perfect example is the stretching of a rubber band. The elongation causes a deformation which results in storing of energy in the rubber band. This is strain energy. Once the applied force causing the deformation is released, the rubber band comes back to its original shape. Think also of our very initial example of archery. What is happening? While there is great variety in the construction details of bows, both historical and modern, all bows consist of a string attached to elastic limbs that store mechanical energy imparted by the user drawing the string. This form of energy is called strain energy, and it is the result of work having been done in stretching or compressing the spring against the stiffness of its material. Like other kinds of mechanical energy, strain energy is potentially recoverable when the spring is allowed to return to its original free length. We know that the amount of work required to stretch or compress a simple coil spring from its free length is given by K times x squared over 2. This amount of work is then stored within the material of the spring and becomes its strain energy, where S(E) is the strain energy in joules, J, of a coil spring, K, is the spring modulus in Newton per meter, and x, is the amount of elongation or compression in meters. It is a fundamental principle that underlies many engineering applications, from the design of bridges and buildings to the analysis of materials and structures. Let's apply these concepts to solve engineering problems. Dr. Lorenzo Garcia here, thanks for watching. Ciao.